So previously we introduced the stack, and we used the stack data structure to implement a interruption processing program for the operating system of the LC3. One important example is that when you run a user program here, some device can send you an interruption. For example, the device can send you an interruption. And then the CPU can go to the routine to meet the requirements of this interruption. And during this routine, there can be another interruption sent by device C, and the CPU can go to this routine in the middle of this meeting for device B. So after this routine is completed, the CPU will go back to CPU. After this is completed, and the CPU will go back to the program main. So you can see here is a stack. First, this one will be pushed into the stack, the top of the stack, and then this one will be pushed into the top of the stack. But this one will be pop out first, and then this one will be pop out. You can also use the stack to to complete some other applications. For example, the arithmetic operation. So instead of some register, some instruction set architecture can use a stack for the source and the destination operations. For example, a zero address function. Zero address function means there's no register at all. In a zero address machine, the addition can be done by a stack. For example, an addition instruction pop two numbers from the stack, add them, and push the result back. So here is an example of how to compute this equation. So for this equation, there is two additions and one multiplications. So first we push A into the stack, and then push B into the stack, and then we push C and D into the stack, and then we do the multiplication. So to compute this zero address machine, break this A plus B, and one of the components plus then the multiplication. By using the stack, we don't need any register. It's very convenient to compute the part by the part. And the algorithm can be implemented a structure of a function, first in, first out. So here is the add operator. First, we can pop. If we cannot do this, then we can finish. If we can do the operation. Which is that we pop one of the operands of this addition. And then we will do the second one. If we still can do it, then we do the addition. If we can do the addition, we will put the result into the. If any of this push pop, it cannot be done, we do the return here. So here is the assembly code for the implemented in a zero address machine. So this assembly code is actually used to implement this diagram. So we have a lot of tracking here. The first track, the second, and then track the addition. So in this way, you can implement various data flow diagram. If everything here is here is another example for the stack-based computation. In this example, we can do the conversion from the ASIC to the integer data. So basically, this program can read some ASIC character from the keyboard and then convert it to the integer. So you can see this. The type means receive one ASIC character from the keyboard. And then we can move it to the register 1. We receive another character from the keyboard and display and we do the addition between the first one and the second one, and then output the result, output the sum to the monitor. So if we give the first input 2, second input 3, output is 2. So this is not correct. Why? Because we directly add 2 ASIC data. So in order to get the correct result, we need to convert the ASIC 2 to the integer 2 and ASIC 3 to the integer 3. There is a constant offset between the ASIC data and the integer data. So we need a program to do that. So this program works to the ASIC binary data. Assume that we can read these three ASIC two digits, and we write them into some memory buffer. And we can use this method. So these three digits actually decimal number, which is 259. But in the memory, we store them as ASIC data. So this is two symbols, a symbol of 5 and a symbol of 9. First, we need to convert this value to its binary form and then multiply 100. And then we need to convert this number to 5, binary 5, and then multiply this by 10. And then we need to convert this number to the binary of 9. And then sum these three components together. So in this way, we can convert three ASIC data here into a binary form of this number. Because the LC3 cannot support multiplication, so we can implement the multiplication by looking up a table. The table can be implemented like this. The first entry indicates 100 multiplied by 0. Second one indicates 100 multiplied by 1. So instead of doing a multiplication, if we have 9 multiplied 100, then we can directly look up the tenants of this table. So we can use the binary form of this value to look up that table, and then we can get the multiplication results. So here we just define the lookup table. First, we assign the starting class of this table to R1. How can we look up this table? We just simply add the index to this graph, to the base of R1. So if we want to visit or look up the fifth of this table, we just add 4 here. If we want to look up the first, actually here you just add a 0. How to do the lookup table? We just load this load instruction. So here is the complete program to convert the ASIC, 3 ASIC digits to its binary representations. first here we do some to clear all the results and initialize some register. And then we process each message digit one by one. We use the digits to look up the tables here. So eventually we can add all the values together to have the results. So after we have the program to convert 6 digits to its binary representation, we also need a program to convert the digit to convert the binary to its basic representation. So this program can help us to convert a 2's complement binary to a 3-digit ASCII number. And then we can display this number on the monitor. So in the purest program, we do multiplication. Here we need to handle this division. We need to perform divide by 100 operation to get the numbers here. Can we still use the lookup table? The answer is no. Why? Because for the number from 0 to 99, if we use this number divided by 100, the result will be always 0. So a lot of a number will generate the same result. In this way, it's very difficult to implement a lookup table. Then we can repeatedly do minus 100 and count how many 100 we can do the subtraction. So in this way, we can also implement this theory. So first, before the conversion, we need to check whether this number is active. How can we do that? We just simply read the first character, whether this character is plus or minus. So this is the assembly code to test the first character. We need to load the data to R1. And then we test whether this data plus or minus. So if it's a plus, then we need to directly to do the computation. Otherwise, it's a minus value. Because that's a 2's complement number, we also need to do some processing. We basically use this loop to compute the division. So there's no lookup table at all. And then in this way, we can implement the conversion from the binary to the ASCII to Any question? So it's very easy to implement this by Python. The library of these high-level language may even support automatically do the conversion, but it's very difficult to do that in assembly language. You need to do a lot of pre-processing and post-processing to support the conversion. So we finish all the lectures on low-level assembly language. So from this lecture, we will focus on the C language. So the aim of this C language is that we can create some compiler to compile this C language into the assembly language, which can be supported by the LC3 simulator. In another word, you can run. We will provide you a compiler so that you can compile the C language you write into some assembly code, and then you can compile that assembly code on the LC3 simulator, and you can run that code on the LC3 simulator. So in this high-level C language, you don't need to handle the register anymore. You don't need even to know how many registers are there. You can directly declare some variables, integer, floating point, and then do your operation. So the compiler will automatically provide some instruction of underlying hardware. For example, you can directly run this equation in the C language. Although the LC3 does not support a multiplication, the compiler will translate line into multiple assembly language supported by the LC3. But the multiple assembly language sentences will implement the same function of this one. So in the C language, you can directly write if else. In the assembly language, you have to manipulate the register labels. There's no clear structure of this. You have to use multiple registers to implement this jump. At least in this structure, there are 2 jumps. And it's very easy for you to read the C language. And there will be less bugs if you write a program in the C language. For the high-level language, there are 2 compilation method. The first one is interpretation. So if you write Python, per least some script language, you will use this method. This method will not compile, will generate any binary code. Instead, when you run that particular sentence, the interpreter will translate that sentence into some predefined library sentences supported by these language. So compared to the second one, this one is slower. But this one is more powerful. For example, you can directly declare a figure and use only one sentence to show that figure on your screen. But you can never do that by the compilation. The compilation means that the compiler will translate your program into machine language or even the binary code. In this way, you have to write all the low-level functions by yourself. There is no library support for the second one. Only some very basic functions provided by the library. But there is no high level for these languages. If you want to show an image on the screen by writing C or C++, at least you need to write maybe 50 or 100 sentences in your code. But for the Python, only one sentence is good enough to do that. The advantage of this one is it's fast. You need to do a lot of low-level job, but the speed of your code is very fast. And the advantage of this one is it's very convenient and it's very powerful. One sentence can complete a very complex job. But the speed is low, is small. So here is the flow to compile some code. First, you need to have some C code, C files. The file ending with C is a typical C file, and the file ending with H is the header of the C files. You can declare some functions, some variable in the header file, but you need to write a main function in the .c file. And when we have all the source code to build the symbol table and then do the target code synthesis. Eventually, the linker will generate a binary. And the linker can also help you to run some other functions provided by operating systems or other commercial libraries. For example, in your code, you can narrow the timing by the function provided by the operating system. Compared to the assembly language, the compiler of C is powerful because it can help you to check the errors. This is so-called source code analysis. If you declare some variable and you didn't use the variable in the following sentences, the compiler can give you a warning. If you didn't declare that variable, but use that variable in the following sentences, the compiler can give you error in this case. So the source code analysis has nothing to do with the instruction. If you compile your code on LC3 or on some Intel machine, the source code analysis are the same because it only checks the semantic meanings of your code in this stage. In this code generation stage, the compiler needs to know the details of your machine. Because in this stage, the compiler translates the C language into the assembly language and the machine language of your machine. If your machine supports the multiplication, then the compiler can directly use that binary instruction. If your machine does not support, the compiler needs to translate that sentence into maybe a function. The compiler also needs to build a symbol table here. The symbol table actually is a map between the symbolic names and items. So we also have this table in the assembly language. But in the assembly language, this is implemented by the assembler. So here is one very simple example of the C language. First, we remove the header file. In the header file, we can define some existing functions. For example, this scanf function is actually defined by the SPEIO of image. So you can think about this scanf. This scanf is similar to the trap X23 assembly code. Both of them can receive something from your keyboard or some file. You can see that you don't need to worry about the register here or the trap instruction at all. Just simply use this sentence, you can receive something from the keyboard. And the printf also is, you can print out sentences like this directly. So compared to the purest assembly code, we need at least 5 sentences to implement this function. But here, just one line, you can achieve the same function. You have to define a main function in your C code. This main function is the starting point of your program. Your program will always start And you can also write comments here. The comments will not have any impact on the final compiled binary data. But it can help you to read your code. So this pattern actually complete. You can also write your own header file. You can define some marker like this. So before the compilation, the compiler will replace all the stuff. All the stuff in your code. As you just declare that the stuff is actually equivalent to 0. So this one can help you to make your code more readable. If you change this value of this stuff, what then you have to recompile your code. You can use this symbol, to declare your comments. And your comments can span multiple lines. It's similar to the assembly code. Again, the most important function of your C code is the main function, because your program always starts from this main function. You have to name the main function like this. You can also add some parameters. We will talk about that. And you have to write all the program within this range. In the function, you can declare some variables. Each variable needed to have a tab. The tab can be an integer or single procession floating point or double procession floating point or some chart. And all the tabs supported by C can be defined by the C library. So the C standard library provides some basic functions for the I/O. For example, the printful, you can actually print something on the screen. This symbol means a placeholder for this variable. And this symbol indicates you need to change a new line. You need to have a new line after this. This is also a placeholder for this variable. After it receives some input, the value of that input will be assigned to this variable. So inside of directly use this variable, we add this symbol here. This symbol indicates the address of this variable. We can add multiple placeholders here so that we can have multiple variables in one sentence. The placeholder is actually defined by the type of the variable. Different types of variable need different placeholder. For example, this is a decimal number, this is a hash number, this is the floating point number, and this is the ASCII chart. All these four sentences implement some print function. And we can use the same placeholder to indicate different numbers, different variables here. For example, the first one is a very simple integer. For the second one, we write an equation here. The compiler will compute this for you before the running, which means that actually after the compilation, the compiler has already computed this equation. When you run this sentence, the CPU will not compute this again. It will directly output the value. And the first two are decimal. The third one is a hex. So you can see that although the decimal of this equation is still 102, but in the hex format it's 66. And then we can output this value as a ASCII2 character here. It's an F. So it's very important to write the correct placeholder here. Otherwise, you will output something you do not want to show. The same as the printf. The most important for the scanf here is still the placeholder. You need to use the correct placeholder. For example, if you want to receive a correct, you need to use this. If you want to receive a floating point, you need to use this. These two are two decimal. After you complete the writing of your code, you can do the compilation. You can use PCC or ICC or CC to do the compilation. Besides of so the compiler period is very powerful. Besides the basic compilation, it can also help you to optimize your code. Any question? Yes, here is the example. if you use the C as the output, no matter the type of your variable here.
Input by using number and this percentage and the first line or second line.
Assume that you have enough space for the variable to receive the thing you want to receive. But when you print the variable out, it's going to give you a track if you use the C here to receive. So this lecture is just give you a very simple starter for C. We will talk about C language more in the following lectures. If no question, we can stop today. Thank you very much.